and welcome to Coderific. In this video, we are going to train a deep autoencoder network that we built in previous video on MNIST Dataset in Keras Python. Let's jump to programming. I'm back to my Spyder editor where I have already included the model that I built in my previous. I have put the link to this video in my description box and I prefer you to watch that video before continue watching this. As I told you before that I'm going to train this model on MNIST dataset. To do that, first I'm going to load MNIST images. I have added a link in my description box where I show you how we can read MNIST dataset images using TensorFlow Keras datasets. So to upload the dataset from TensorFlow Keras datasets, I have imported the dataset from MNIST.mpc variable, and it has exported all of the 4 subsets, and to carry those subsets I have created 4 variables. To train a model, if an image is in float format, that will be great. The network learns very well on float dataset or float format of image. So here I have created values of pixels in my train images by dividing it to 55. I have created the float dataset, and similarly I did this with the test dataset. And remember that autoencoder always takes as input an image and predicts an image, so we don't need the labels of images. That's why I have assigned whatever I have in my train dataset to ytrain, because my input and targets are same. There are images of same size, 28 by 28 by 1. Y1 because the color channel is only grayscale. Similarly, I did this with test dataset and assigned it to my white dataset so that the X test and the target values for these subsets are same. Before I compile my model, I have defined my optimizer, that is SGD, which is stochastic gradient descent. I have imported it using the TensorFlow.keras.optimizers, and for this optimizer I have used 0.1, and I have kept the same decay, momentum and other variables as it is as we find it in on Keras optimizer page. So I have assigned this optimizer a variable which is SGD. Using this optimizer, I am going to compile my model. For loss, I have used mean squared error. It will simply compare predicted image with the ground truth image or the original image, and optimizer I have passed SGD, which I computed here, and I have kept the same variable as it is. After I have compiled my model, I am going to fit the compiled model on my X-train dataset and the target values. I'm going to run my model up to 10 epochs, batch size 128. I'm going to keep the shuffle true. By keeping the shuffle true, it usually gives us a training loss minimum. To keep an eye on my training errors or training losses, I have used validation dataset so that I can compare the train loss with validation loss to see if my model is facing overfitting or underfitting. And to do that, I have not created validation dataset separately. Rather than, I have used only 20% of my train dataset as validation split. When my model is training, I want to see how much time did it take to train. To do that, I am going to import a time library, and I want to see the timing of only the training process. I have not included the compiling time or the data preprocessing. So right before model.fit function, I have added the time.time. It start the clock right before starting the training, and right after it finishes training, I am simply going to take the difference of current time and the start timing. I am going to run the program written so far. You can see in my Python console that the training of my model is complete, and total of seconds it took to train is this number. If I divide this number by 60, I will get the duration in minutes. So my model took 11 minutes and some seconds to completely train. And if you can see on the last epoch, the loss and the validation loss are very close, almost similar. It says that there was no case of underfitting, neither of overfitting. So I will add a link to a very good post to Stack Overflow that says about the loss and the validation loss difference. Also a link for how to solve the cases of either underfitting or overfitting for your model. So for me, in most of the cases, this setting of SGD works better than others. So if you are trying or if you are struggling with validation loss or the training loss, try this setting of SGG. I hope it will work for you too. So now my model is trained. I am going to predict my X test. I'm going to run this line. As you can see in my variable explorer that the expert dimension has added one extra dimension at the end, but to compare the evaluation over the X test, I need to remove these extra one dimension by reshaping it. So basically I have kept the dimension 0, 1 and 2. So now you can see that the extra dimension has been removed. Now it's in perspective shape. Now I am going to take the mean square error over X prediction and X test datasets. To do that, I am going to first create a function that is going to simply compute the square root error over the mean of predictions and targets. I have called the function that I just created and pass this function xtest and xpredicted dataset. At the end, I am going to print this value. Let's run these lines. RMSE value, which is root mean square error, is 0.12. If this value is closer to 0, the better. This is it for this video. Thank you for watching. I hope you find it helpful. If you did, do like and share. Also subscribe the channel and hit the bell icon so that you get notified whenever I upload a new video. If you have any suggestions, leave them in comments section. I will do consider it. Thank you.